Hopefully everyone's not too deep into their post-launch food coma, but let's get started right away. Yeah, thanks, Nell. My name is Mark. I work on the API infra team at Netflix, and I live here, so it wasn't too much of a trek to get here this morning. Before we start talking about a tracing crate, who actually uses the tracing crate actively in production right now by show of hands? Cool, that's awesome. Okay. Great. So my goal is to kind of like give it a little bit for everyone. For those who've never heard of it, we'll try to give it a little intro. And for more experienced users, hopefully you get some tricks or relate to some kind of weird stuff we've done. So for context, my team works on a layer 7 gateway. That's the kind of the entry door for most of Netflix APIs, consumer-facing at least. And we use this thing called GraphQL Federation. If you've never heard of GraphQL Federation, it's this thing where our various domain teams can own part of our API surface and register part of their schemas. And then our layer 7 gateway that I was talking about query plans these queries, dispatches to the right services, merges responses together, and sends back to the client. We like open source, but all this stuff so far was built using in-house tooling and our own implementation of the federation spec. Recently, this company called Apollo released this new GraphQL Federation router. It was written in Rust. I had been using Rust for my own pleasure before, so in a very non-biased way, I agreed to give this router a try. But this router contains the engine for GraphQL Federation. But as you can probably guess, there's a lot more that goes into building a High-RPS server at Netflix. There's a lot of stuff to rewrite in Rust, unfortunately. Stuff like instrumenting your application was another big one. Apollo router is built on Tokyo and uses the tracing crate to instrument their code. We also looked at the tracing crate and thought it was quite interesting for our own telemetry around the router. So if you've never heard of tracing, we'll do a little brief tour. But first, I really want to thank the maintainers of that crate. Some of them helped us a lot. Special thanks to David and Hayden that helped us very early on, and Eliza for the implementation and some of the funny comments in tracing's internals. So tracing allows you to instrument your application with spans. Span represents something that has a beginning and an end. Within those spans, you can emit events that are also structured events that you can emit within a span. By default, these spans and these events are pretty inert. They don't do much. Instead, you need a subscriber to listen to these things and do something with them. If you're like us, these events and spans don't go exactly all the way to the same place. For us, we had existing logging systems through TCP log thing that we use. Metrics go to this in-house metric thing we have called Spectator, and we send our distributed traces to Zipkin. So in practice, one subscriber would maybe be a little annoying to build. And this crate tracing subscriber helps you compose multiple layers into one subscriber. Actually, this is kind of literally what our subscriber looks like. It's a tracing subscriber registry that has logging using tracing's built-in FMT layer, metrics and tracing using the tracing open telemetry. So we set that up. Everything was going fine. And then we like to profile our stuff pretty often. And the first flame graph I took looked something like that. This one is a little fake because I forgot to save it, so I kind of reverted a bunch of stuff to show what it looked like. But we were seeing like 10 to 15% CPU spent in tracing. And it wasn't actually just publishing those events. It was all these other kind of like more internal functions that tracing has. So we thought, OK, this is great. Everything works. But can we actually make this stuff cheaper? And to understand how we did that, I want to spend some time talking about the hierarchy of what you can do in tracing and how much overhead it brings. And since this is going on YouTube, I thought maybe I'll do like a tier list thing. Apparently for engagement, it's good, but I'm not actually going to do that. Instead, I kind of want to walk through what happens when you use those tracing macros that we use all over the place. And we'll do that in reverse order. So at some point, your subscriber gets an event. That's where you'll do something. Like for us, that's batching those events and sending them through a TCP sync, but that's your kind of like user code. That obviously has the highest cost. We want to avoid that if it's not necessary. So your layers in your subscriber have another tool to filter events before you get there. It's called event enabled. And notice how the function signature here gets an event. This event is a fully formed event with fields, their values. So we can use that function to filter through a lot of dimensions, but it does have a cost. So if you don't want to pay that cost, there's this enabled function. And notice how it's not an event we get anymore. It's metadata. And this metadata is completely static and contains information about where you submitted that event. So that could be like the line number, the module it was published in. So this allows you to do filtering that has not yet had to do the work of like building the event, evaluating the values, things like that. Enabled still has a cost if you call it for every event, right? Depending on your logging level, we have events that are published many, many, many times per request. You can imagine even we have Tokyo with the tracing feature enabled that has extremely frequent events. So this is where tracing really shines with this concept of a call site. Every time you use a tracing macro, a completely static call site is created for that event in this case. And this call site, the first time this log here, our hello, is called, the call site will ask your subscriber, what's your interest in this event, statically? Your subscriber will respond with one of three values. One is never. That's kind of the easiest one. Your subscriber will say, you know, this trace event deep into Tokyo, I never want to do anything with that stuff. Going further, this static call site will remember that and never call anything further with this particular event. Always is kind of the opposite. It means don't even bother filtering that event. We know we always want to publish it. So skip the overhead of verifying anything. And maybe the more interesting one is the sometimes, where we're asking the call site to always check with us whether this event should be published, which would continue to what we just seen with the enabled and event enabled. If this still has too much overhead, and it's called once per event, tracing also gives us two other tools. One is called max level hint. The other one is static max level. Static max level is literally a compile time. You might say, I'm never interested by trace level events. Like, don't even include them in my binary, which can be useful. And max level hint is a way for all your layers to agree, in this case we had 3, on the max level they want to see, and kind of like, yeah, agree on something they'll all not be interested in. And that's not a compile time. So, recap quickly before we continue. Less overhead is anything that's closer to compilation, right? So that starts with the static max level to probably in practice using that call site caching technique. And then the stuff we want to avoid as much as possible is actually publishing the event. So it's all about minimizing runtime work. And just a little plug here, I absolutely love this paper if you're interested in that kind of stuff. This paper goes like even further into how you can use compile time techniques to avoid runtime costs for logging. OK, in practice, our filters might be different based on our layer. So we might need to filter certain call sites for metrics, for logging, for tracing. And you can totally do that with another layer that would filter these out. The problem is that if a layer answers never, it answers never and short circuits the entire chain. To solve that, tracing gives us per layer filters. So you can combine a layer with its own filter that will act only on that layer. Combining a layer with a filter gives you a filtered struct. But you might ask, OK, but how does it work? Because we just saw if something answers never, it kind of short circuits the chain. And there's a pretty interesting technique that goes on there. So when you use per layer filters, every filter will say, yeah, always, just keep going and ask the others. But we'll kind of secretly register the real interest to this filtering thread local. The registry is then in charge of combining these interests and actually returning the real one. As you might assume, this can be a little finicky sometimes. For example, we were using the metrics layer from tracing OpenTelemetry. The metrics layer is not actually a filtered, but it's a struct that has this inner filtered, and it delegates filtering decisions to it. We were seeing a bug where, even though it was filtered, we were receiving events for all our layers, as if everything was enabled. Dug into tracing code, and I saw this struct, and I was like, nah, this looks totally fine. Probably not the issue, right? It turns out that one of the ways tracing uses to check whether something is a per layer filter is to try to downcast it to this thing called a magic PLF downcast marker. If you go back here, the metrics layer, even though it acts perfectly well like a filtered, it actually isn't a filter struct. And it doesn't downcast to this magic thing. So we forked the metric layer. This bug actually still exists, I believe. We forked it temporarily to fix it, and we instead decomposed it into an actual metrics layer, an actual metrics filter, used the width filter to get an actual filter struct. And there it is. That was the issue. We instantly gained, I believe, 5 to 10% CPU for that simple fix. So here's a few practical considerations for using tracing. It's kind of lessons we've learned over the past few months. First one is what we just saw. Make sure your per layer filters are actually filtered structs. Another tricky one is that spans usually by default assume kind of a tree-like structure, right? You start a new span, it's the child of the current span. That might not always be what you want for certain spans. For example, really early on, we found a bug in tracing in Tokyo with a tracing feature where certain mutex spans that we were holding in a cache were keeping all parent threads, all parent spans open. So fixing that helped greatly, obviously. Be aware of surprise-enabled calls. So we saw earlier on that per layer filters kind of combine together to give the real interest. So if you're decoupling your different layers and you have a logging layer, you've implemented register callsite and you return never, it might not always be the case that it will be never if somebody adds another layer, for example, that says always. So always make sure that your register callsite agrees with your enabled method that might be called at runtime. Another one is that the tracing OpenTelemetry crate might not be doing what you want it to be doing. First of all, by default, it just listens to every span and every event. If you're like us, where our distributed tracing is a little bit more fine-grained, we're not necessarily interested by every event and every span. That would be way too expensive. We've opted for sometimes very simple approaches of allow listing things we're interested in. And this is all static information, so we can filter out things we're not interested in very quickly. The other one is that it's confusing sometimes, but OpenTelemetry spans that you're exporting, while they're linked to tracing spans, they're not the same thing. So OpenTelemetry has sampling, but the tracing spans might not be sampled. So we had to kind of circumvent, and it's not actually a great solution just yet, but we let the root span go on, let OpenTelemetry make the sampling decisions, and kind of try to disable everything else after if we're not sampled. Consider not using mFilter. So if you've used tracing before, mFilter is a pretty powerful tool. It lets you have these directives that describe what call sites you want to enable. As you might have seen with previous slides, sometimes, depending on what you want to select on, some things have more costs, some are tricky. There are a lot of known bugs with mFilter as well. So for us, we've opted for something a little bit more specific to your use cases. For example, we like to have a base level for most events, and then kind of like in a fine-grained way, enable targets we're interested in. This allows us to First of all, we'd never allow filtering on values of events, for example, because we think that's probably too expensive at runtime. So just a little bit locked down version of filter. The other trick we had is we prefer to use field names over values when possible. Because values are often expensive to look at even, we prefer trying to express our call sites using field names. So this is an example, for example, where instead of the one on top here, instead of having to filter on a value for service name, we'll prefer maybe having multiple call sites that we can enable in a much more performant way. We found early on that all these things were a little flimsy, and we'd often see like our canaries returning, hey, you've just bumped CPU by 10% because somebody added an event in some place and it changed the interest for our global subscriber. So there's a query called tracing mock that is absolutely useful to test what events are published. What we found was missing is testing the static register call site technique. So we have this verifying subscriber thing, which we have to run in integration tests because it's kind of a per process thing. But we verify very simple things like this trace event should always be never. And we actually caught a lot of regressions using it. So after all this, we got down tracing to about 1% to 2% of CPU for our app. Most of it is whenever a trace is sampled and we publish the event. So at this point, you might be saying, OK, well, you're just doing nothing now, which is true. But doing nothing sometimes is pretty hard. So we were pretty happy with this baseline. But we did want to get some information out of our servers sometimes. It would be great to have almost no overhead when nobody's looking at our servers, but sometimes just get something out when there's an issue. And issues can be anywhere, so we'd love to be able to inspect this crate that we're using, or in our code, just really any call site. We were inspired by this system called Mantis we have at Netflix, which allows applications to publish objects to a JSON stream, but that have no cost unless somebody's listening to that stream. So whenever we have this UI where somebody can register with a SQL-like language that asks our servers, hey, start publishing these events that have this field, that kind of stuff. So we wanted to kind of achieve the same thing with tracing in our logs. And it turns out tracing allows you to do that pretty easily. Call sites are able to be reloaded. There's this public function that allows you to tell every call site, hey, call site, please ask the subscriber again if the interest has changed. It goes through every call site in your program and rebuilds the interest cache. In practice, there's even a layer for that called reload layer, which allows you to swap a layer for a new version of the layer and rebuilds all call sites. Obviously, that's not free. In practice, though, we found the overhead is fairly minimal. So we use it heavily, and we really haven't found much of an overhead with this. Your mileage may vary. So this allowed us to modify our config at runtime, add targets, add filtering on events based on their field names, that kind of stuff. The thing we wanted to add here is, OK, yeah, I can add more call sites, but what are the call sites to begin with? We use a lot of crates. We have a lot of logging. It's pretty free now that we have this filtering to add more events, more traces. So we built this kind of meta subscriber that just delegates to the other subscriber, but just keeps track of the call site. The call site has metadata that it can give us, like the file location, log level, even the unique ID we'll get back to. This unique ID is an ID all call sites have. Right now, and this is kind of an internal bit, so it's a little chaotic, but this is the memory address of the call site. So we thought, oh, maybe we can actually use that thing to filter. And that call site allows us to do more fine-grained than, say, a module, for example. But for some events, like logging response bodies we were getting, that was still too much. So we also introduced sampling to this directive. In practice, we don't actually reload files, and we have this system called fast properties. They're basically properties we have in the UI. We can set them, target them pretty precisely to an instance, a cluster, for example, and the instance reloads with these new properties. So let's say we have an issue with Hyper, and we're not sure what happens when we stream the body. We can find out where we want to look at, like this debug log here, check what the call site is for an instance that's having issues, get the identifier, and then create what we call a fast property for that particular instance. Here I'm setting it to debug, so I want to see it at the debug level, and I want 10% of these events. And then we just start getting that fire hose of events. And this is awesome because we can do sampling as low as we can. Sometimes we basically never want to log response bodies, that kind of things. So yeah, this lets us see very, very fine-grained things. And this is a very low cost, basically just reloading call sites. We actually tried maybe reloading one call site. Tracing public API doesn't let you do that at the moment, but potential optimization. So overall, the key to using tracing, in our opinion, is to get rid of stuff early, get your call sites in the right place, and then allow your engineers and anyone who wants to look at what gets out of the box to surgically enable certain call sites at runtime. So hope that interested you. If you have similar experiences, want to chat, please hop in Discord. We have a channel, or just meet me in the hallway or outside. So thanks, everyone.